Hello, welcome to Backer Breaks It Down. In this episode, we are going to look at radii and chords of a circle. We're going to identify and describe some relationships between these two. And previously, when we last met, we investigated radii and chords. And so we've already kind of discovered all of these relationships. But in case you have forgotten, well, I'm going to go over them one more time. So a chord of a circle. A chord of a circle is a segment, and the segment connects two endpoints on the circle. Okay. A radius of a circle is the segment that connects the center of a circle to a point on the circle. And so these relationships that we work with here are dependent on this first relationship between the radius and the chord that says the distance from the center of the circle to a chord is the measure of the perpendicular segment from the center to the chord. Okay, so if you look at this diagram over here on the right, we're talking about like the segment OP. OP is that perpendicular segment from the radius to the chord. Okay, so recall perpendicular. What that means is that where these two segments are meeting, they're creating a right angle. Okay, and knowing that is going to help us apply these two theorems. So we have the Radius-Chord theorems, and they all essentially say the same thing. If a radius is perpendicular to a chord, then it bisects the chord and the arc. Okay. All right, so it could be the diameter, but if it's perpendicular to the chord, it bisects the chord and the corresponding arc. And we are seeing that in this diagram over here. They're saying if segment AC is perpendicular to BD, right, and we're seeing that because of that little right angle box there, then BF and FD are congruent to each other, and arc BC and arc CD are also congruent to each other. The radius of a chord bisects a chord that is not a diameter, then it is perpendicular to that chord. So this second theorem here is essentially just the reverse of the first one. The perpendicular bisector of a chord passes through the center of the circle. Yeah, so all three of these are essentially like saying the same thing. The equidistant chord theorem says if two chords of the same circle or congruent circle are congruent, then they are equidistant from the center of the circle. And so this diagram over here on the right is illustrating that. They're saying if chord AB is congruent to chord CD, then EG equals FG. Notice EG is the distance chord AB is from the center, and FG is the distance that chord CD is from the center. Okay, so congruent chords means they're equidistant from the center of the circle. So now let's take a look at a few examples that use these theorems, because we want to be able to apply these relationships in problems to find like missing measures and segment lengths. Right. So here in problem number 1, it says circle O has a radius of 13 inches. Okay. Now I have drawn in one of the radii of the circle. Just remember that all radii of a circle are congruent. So OC, which they've drawn for us, is 13. OD would be 13. OB would be 13. Okay, all radii are congruent. Radius OB is perpendicular to chord CD, which is 24 inches long. So chord CD is 24 inches long. Find OX. Well, the fact that they're telling us that the radius is perpendicular to the chord, we can conclude that it bisects the chord, right? So what that means is that CX is congruent to DX. Together, they make that 24-inch long chord. So that means each of them would have a measure of 12 inches, right? Now remember, the radius of the circle is 13, and OC is one of those radii. So I know that is 13. Now we want to find OX, right? So I want to kind of like show you something here, okay? This is what we want. We want OX. We know the radii of the circle is 13 inches, and we know this segment of the chord is 12 inches. So look at what we've got here. Yeah, that's a right triangle. And as you know, in right triangles, the three sides are related by something called the Pythagorean theorem. So I can totally use the Pythagorean theorem to find the length of OX because I have a right triangle and I know one of the sides is 12 inches long and I know the other side is 13. So I can just use my Pythagorean theorem. X squared plus 12 squared is 13 squared. And I can do the math. And that math is going to tell me that X is equal to 5. So therefore, OX is 5 inches. So that's something like we find ourselves using quite a bit with these types of problems. Is an old favorite, the Pythagorean theorem. Problem number 2 says two circles intersect and have a common chord 24 centimeters long. So let's talk about this common chord that they speak of, okay? So remember, a chord is a segment that joins 2 points on a circle. So I'm thinking we should draw in this common chord that they're talking about, right? So they're talking about this chord, oh wow, right here. That common chord is 24 centimeters long, okay? They also say that the centers of the circles are 21 centimeters apart, okay? So I'm going to get out another line tool. And they're saying from here to here, that is 21. And the radius of one of the circles is 13, okay? So let's throw in those measurements and kind of like see this a little bit more clearly. So that common chord is 24 centimeters long, right? And so we're talking about that blue line that I drew there, right? The centers of the circles are 21 centimeters apart. So from here to here, that's 21, and the radius of one of the circles is 13. Now, they don't really tell us which one is 13, but we can just pick one. Yeah, we'll just go with the bigger one. Okay, so we'll say that the radius of this circle over here is 13. So we know the radius is 13. Since the common chord is 24 centimeters long and the radius would bisect the chord, we can say that each segment is 12 centimeters long. Okay, and so once again, Pythagorean theorem, do you see it? It's like right here you have 12, unknown, and 13. So we've got this right triangle here. And so we can use Pythagorean theorem to find the missing measurement. But this is like the same two measurements we were working with in problem number 1. So like I know that this segment then would have to be 5, okay? Because 5 squared plus 12 squared is how you get 13 squared. And because I already did the math in problem 1, okay? So remember that whole distance from center to center was 21 units long. We just determined that one of those distances is 5. So what does that mean, the like other distances from here to here? Well, 21 minus 5 is 16. So this distance from the center to the chord is 16. The segment of the chord is 12. And so we want to find the radius of the other circle. And what do you know? We can use the good old Pythagorean theorem. So we can say the radius squared plus the other leg squared, so 12 squared. Oh, wait, no, wait, that's not right, because the radius is the hypotenuse. Sorry about that. So 12 squared plus 16 squared is equal to the radius squared. And then we can use a calculator to help us determine those things, right? So 12 squared plus 16 squared is 400. Which means that the radius would have to be 20. Okay, So once again, Pythagorean theorem, we used it twice in this problem. Yeah, it's a good thing to know. The last one has us using the equidistant chord theorem, obviously, because I have it at the top of the screen. But how do I know that that's what I'm using? Well, let's check it out. So in circle O, find CD if PA is congruent to QA. Okay, so that's what we're given. And so anytime we're like given something like that, we should be like, well, what can we conclude from that? So the PA and the QA, they're referring to the two distances each chord is from the center of the circle. Okay, and so we know that two chords are congruent when they are equidistant. So because we were told they were equidistant, we can conclude that chord CD is congruent to chord XY. That's what we can conclude. All right, and we want to find CD. Ultimately, that's what we want to find. So we know a few things. We know that dp is x squared plus 20. So dp is just this part of chord CD, but we do know it's x squared plus 20. And we know that xy is 21x. So xy is the entire other chord. Remember, okay, so we know that x, y, and CD are congruent. So we have part of our equation here because like we know what x, y is. We know that x, y is 21x. But what is CD represented like algebraically? CD, the entire chord, is going to be equal to 2 times the PD segment. So 2 times x squared is 2x squared. And then 2 times 20 is 40. So what we have here is a quadratic equation. Okay, and we're going to solve this by factoring. So in order to solve any quadratic equation, you have to first get it equal to 0. And so I'll do that by subtracting 21x from both sides. Okay, and then once I have it equal to 0, I can go about my chosen process, and I've chosen to factor it. Remember to always look for common factors first before you go doing that AC method. To save us some time, I've already done this. Okay, so there's all my algebra, right? And this is what I ended up with when I was all done factoring. I had the quantity of x minus 8 times the quantity of 2x minus 5 equals 0. And so if I use my zero product property, what that means is that x is 8 or it's 2.5. And given the representations of our segments, both answers do work. So we have like two possible answers. So if x is 8, CD will be 168 units long. And if x is 2.5, then CD will be 52.5 units long. And so those are our radius-chord theorems and relationships. So just remember, if a radius is perpendicular to a chord, it bisects the chord and its arc. And if two chords are congruent, then they're equidistant from the center of the circle. And that's how Backer breaks it down.